Hi, we're Robotic Fuselage Inspection for Dents and Scratches. I'm Tommy, joined today by my teammates Anael, Ray, Shreya, Hao, and Sanjar.
We will start off with the introduction, describing the background and problem statement we were given. We will go over the requirements for the project and then jump to the implementation where we worked on the end effector, motion path, machine learning, and design an augmented reality app. We will then finish off with the demo of the robot and the AR app.
Background and problem statements before the fuselage is penned and the instruction inspector need to manually inspect the surface to diffuse as such as dents, scratch, and fuselage fasteners. This inspector problem usually take hours, and the inspector walk around the fuselage with flashlights, carefully examine and identify any fuselage using their fingernails. Objective develop the robotics arm virtual system to using Phoenix CRX 20IAL robotic arm and real sense cameras to capture the image diffuse of the fuselage panels, detect and classify the defect using machine learning and virtual classify diffuse and their location on the AI. Next.
So these are the requirements of our project. For the robotic arm, we needed to develop a motion path to traverse and scan through the entire fuselage. Then we needed to capture the images of defects using the Intel RealSense camera and develop a computer vision model to classify those images. And in the end, we had to develop an end effector that would house a key and sensor and a marking mechanism. For the AR app, we needed to scan the object and export it as a 3D model and anchor those 3D models at a specific location. We also had to mark spots outside and locate those at the inside of the 3D model. And finally, we had to display defect locations on the 3D model. Next slide, please. So starting with the end effector part, we used an Intel RealSense camera to capture images of the fuselage. It has a disadvantage that it is unable to detect smaller defects. So it could possibly be replaced by a 3D laser profiler, like a KN scanner, which is able to detect even slight defects on the surface. And the profiler could be attached to the end of the robotic arm using an end effector as shown in the figure. It has a linear actuator with a marker attached to it, and the marker is aligned with the center of the center of the sensor's laser field to accurately mark the defects. Next slide, please.
As for the motion pass, we are using the proprietary software RoboGuide and the third-party software RoboDK to plan a motion pass and scan the entire surface of the fuselage panel. RoboGuide and RoboDK in general, they allow us to create the digital twin of the real workspace, define the scanning paths, configure motion constraints such as collision avoidance, and it's overall allow us to generate a motion program to upload it to the robot and deploy it in the real situation. So before that, but we also need to simulate it and test it for safety and other requirements. The next slide, please. Before coming to RoboGuide, initially the project was planned for year 16, so that's why we used the MOVEit motion planning package and Gazebo simulation to create the digital twin of the workspace. But after changing the robot to FANUC, which is not supported by MOVEit motion planning package, we changed to RoboGuide and RoboDK. RoboGuide, as I told, it's a proprietary software of FANUC, so it's the best option, but also we have a RoboDK, and the cons of the RoboDK are the limited functionality, such as predefined fixed motion planning algorithms, and no option to integrate computer vision. But it has pros also, such as to integrate the user Python code with computer vision packages to train the scanning with the computer vision. Yep.
For machine learning, we use Inception v3, which is a convolutional neural network designed for computer vision tasks such as image classification. Inception v3 is a pre-trained model that was originally trained on a larger data set such as ImageNet, and this is particularly useful for our application because we have a limited data set. So Inception v3 will leverage the pre-trained weights and learning features to improve the performance. For our data set, we mainly consist of scratches and non-scratches. With these images, we pre-process them to be the size of 299 by 299, and to create an additional images for our data set, we rotated each image by 90, 180, and 270 degrees. We also perform data augmentation to artificially increase the size and diversity of our training data set.
For the AR app, we implemented Apple's ARKit and the mesh through Apple's Xcode to be able to scan and generate a 3D model. ARKit provides tools and APIs for object scanning, allowing you to capture the geometry and texture of real-world objects using the device's camera. So we used an iPad. We are also able to upload an existing 3D model and show it in the real world. This allows for larger applications like the whole fuselage or a big surface. So instead of having to scan the whole thing, we can upload the existing model. Or for smaller applications, as well as you can see the cup. In our case, it was the panel, so we uploaded it into the apps library where we can add or remove multiple models. From there, we can bring the 3D model into the real world and use the image detection anchoring, which Hal will talk about.
So for the image detection and the anchoring alignment stickers, to anchor the 3D model to using a real world object, the app will utilizing the image detector technique. We're creating anchoring alignment stickers or markers that can be placed in a physical object. These stickers will serve as a virtual cube for the app to detect and recognizing the object position and the orientation accurately. Next.
So now we're going on to the demo portion of our presentation. Our first demo is just a test program that we initially did where the robot arm will move about the fuselage panel and then eventually mark a test defect. So as you can see right now, the robot arm started at the very bottom left corner of the panel and is moving horizontally and vertically along a certain path that we hard programmed. Now it's going to do a test defect. So now, Ray, you can share.
All right, now I was sharing my screen to demonstrate the app thing. In seconds, yeah. Now you may see my app right now. Here you can see our app have two main features here. The first one is library, and the second one is a scan function here. For library, we can import every 3D modules we needed, and then we can access later in our scan modules here, and we can both import those different 3D models in our app, and then we can rename, delete, and sharing those 3D models in our app within our app. So it's kind of convenient to do different type of file management. And then I will show the scan feature that in our app. You can see for here we have stickers that how talked before. It's alignment anchoring stickers that you can see our app can recognize it, and then it will show a orange. It will overlay orange layer to that. It will show that it recognize that, and then we push this button and just select what kind of model we want to. For right now, we want to use a panel because we have a panel here, right? And then we just choose a scale, and then we can anchoring our 3D model to the real world model here. So it's just like that. You can see as we move, it just can move with our movement. So it's kind of good and of tracking. So we can adjust the scales as we want, and we can change to different models if we need it. For this one, we're using a teapot. And we'll just align this teapot in our stickers. Okay, that's all for me.